Just nice to have Paul here, I don't have to think much. Matti, remember how I cut you off early?
Yes.
The good news is, you've got like an hour and a half to speak now. No, I'm joking. No, you've got at least 20 minutes, 21 to be safe. Have you got enough material?
Yeah.
It doesn't matter if you don't, because when we go to questions, that'll really drag it out. We might finish. Ladies and gentlemen, to look at battery buffer charging. I did that too last time. Where did it start from last time? Yeah. Just keep talking, chatting amongst ourselves. It's good to see the Mercury and the Southern Cross Television, so Southern Cross News tonight. Who's going to the dinner tonight?
Yeah.
Jeez Louise. Okay, $88. I'll read the menu. Actually, I'm turning it into a rap song, so by lunch, we should be able to get you salivating. Delta Energy Systems, please welcome Matti Dinkelmeyer.
Thank you, John. Thank you for the previous speakers, giving us a good insight of what's happening in New Zealand, but also in Canberra. It's a good start. Hopefully we'll have some more success stories around the country to announce. So we at Delta are a manufacturer of hardware, charging chargers, AC chargers and also DC chargers, and looking at smart charging solutions in this context. So just giving you a bit of an introduction. Of course, in Australia, we've got new manufacturers, vehicle manufacturers that have announced vehicles to come into the market. So hopefully we'll see a larger diversity of electric vehicles in Australia, which makes the whole experience more interesting. You know? So also we're seeing an uptake in government departments, fleet operators, rental car companies that are also jumping onto the, or seeing the trend and investing into electric vehicle fleets, growing their own car fleets to include battery EVs or plug-in hybrids. All of that is an important step in the way to a really large proliferation of electric vehicles in the Australian mainland fleet. And also, as we've heard from the previous presenter, utilities are getting more interested in charging solutions, seeing the value that electric vehicles can bring to not only their own product offering, but also as a tool to managing network stability. So, you know, going the risk that this is information that you are also well aware of. Obviously, we've seen longer driving distances, larger batteries, and you know, in the future, next year, Porsche Mission E, for example. I don't know when we are going to see these kind of vehicles arrive in Australia, but definitely the increase in battery capacity will also necessitate larger charger capacity, higher voltages, and the management of these kind of energies are going to be become a challenge in the future. So at Delta we are already thinking about these kind of possible solutions and how to integrate our chargers with the increased demand placed on electricity networks. So different chargers cater for different applications, let's say. So we've got our standard AC charger, which is a 7 kilowatt model. Typically it would be installed in car parks where you have a long dwell time. Let's see an application like if you're going to the movies or a shopping center, those kind of applications. You have a 7 kilowatt car charger. As a next model, we have a 25 kilowatt DC charger, which kind of fills the gap into fast charging, provides a top-up. Usually the vehicles will spend less time in those locations. for instance, could be used in your short distance delivery, your supermarket delivery, your Coles or Woolies that do home delivery, your postal service or small parcel delivery that do a quick run in the morning and come back for a lunch break and charge the vehicle and do another run in the afternoon. So this kind of, as I mentioned, fills the gap. We have the standard fast charger, 50 kilowatt. We've heard before that is already quite prolific in other markets, this capacity. And moving to higher capacity charging, ultra fast charging, starts at 150 kilowatt, and designs for 350 kilowatt chargers are already on the drawing board. Now, typically these kind of high power applications, 150 to 350 kilowatt, you won't just have a single charging gun or two charging guns. You have multiple charging guns and need to cater for simultaneous charging of, in the 150 kilowatt application, six charging events simultaneously, or in the 350 kilowatt application, depending on the satellite stations, between 6 and 10 simultaneous charging operations. That will obviously share the power available. Now, we have also heard that the electric vehicle fleet is going to increase, and with ambitious government targets for emission abatement, we are looking at something around the 2.2 million EVs by 2030, which really necessitates already today looking at where this infrastructure is going to be hosted, what kind of grid or networks it's going to be plugged in, just to make sure the capacities are available in those locations. We look at different applications here. So the long dwell time AC charging station is a fairly straightforward application. Maybe you need some load management on the connection side in your car parks if you have multiple of these AC charging stations installed. But they are, let's say, fairly easy to integrate in the existing grid. Now, once we get into the fast charging infrastructure, and maybe the experience in New Zealand can confirm that, then you definitely need to investigate more closely in what is available in terms of the transformer capacity and what kind of effect that kind of charging has on the load at that particular transformer. So we will have to deal with spontaneous high power draws in those locations, especially if you have large battery capacities and a high power charger, DC charger. That will certainly deliver quite a whack to that particular transformer. Those kind of applications really need to be buffered and load managed. And especially in Australia, as we've seen in earlier presentations, we have many roadside locations that don't necessarily have access to a substantial electric infrastructure that will be able to support fast or ultra-fast charging. For those installations, we need to look at alternative ways of integrating. So we really need to dimension the systems accordingly and make sure that they don't overload the local applications. I've also included in there non-permanent installations, temporary installations that can be shifted around. So looking at different application scenarios in a sense to mitigate any impact negative impact on the grids. So yes, there's a couple of networks already available in Australia. We've seen a big announcement in Queensland as well, where infrastructure is going to be rolled out. And of course, many of those locations will need to look at more closely at transformer capacity and how load management is going to be managed over there. So especially the long distance highways, that is going to be a challenge. So in having said that, we are looking currently at advanced EV charging solutions and what can be done in particular to integrate EV charging in long distance travel. So Northern Europe has similar challenges, although in Australia we will seldom see a situation like this with high snow. Maybe in Tasmania on top of Mount Wellington there might be some occasions where you have this kind of snowfall, but essentially ultra-fast charging stations will need to be rugged enough to handle with all sorts of climatic conditions in remote locations. As we heard before, reliability is of the essence, and uptime is a key point in installing a reliable infrastructure. So what we are looking at Delta is in particular combining the EV charging with distributed renewable energy systems, energy storage, and looking at an integrated solution where in remote applications we don't have just the EV charger, but in effect we pair it with energy storage and renewable energy generation. In Australia that's most likely going to be PV energy. In New Zealand probably wind power or micro hydro, anything along those lines. The idea, the concept is that those renewable energy sources will charge the battery, and then when the electric vehicle comes to charge up at the charging station, the initial whack that the battery needs, or the peak, will be handled by the stored energy in the battery, and thereby reducing the required size of the transformer. So this is something that we've already implemented in Sweden, remote Sweden. You see a beautiful holiday destination or day trip destination with nice grass growing on the roof, using a couple of 50 kilowatt Delta fast chargers, using a 288 kilowatt battery bank, and a bidirectional AC-DC converter hooked into the power grid. So this kind of application is already possible with today's technology. Of course, this can be scaled up or scaled down. In particular, this is something that we are investigating currently for Australia. We all know that in Australia, many people, probably many of you, will have solar systems at home, a PV system, and you may already be considering putting a battery storage on it as well. So for your domestic EV charging, why shouldn't you use your own battery as well to do some microgrid smoothing or something along those lines anyway? This is something we are investigating, and looking whether a 7 kilowatt AC charger, why shouldn't it be paired with your battery storage and hybrid inverter to charge your car? Now, of course, one question here is the battery, what battery chemistries are required to support this kind of application? And so for our delta-specific E5 hybrid inverter system, we are just undergoing a test series with our friends and partners at CSIRO. Thanks, Chris. Thanks. To find out what kind of temperature sensitivity and performance stability can be achieved using standard off-the-shelf hybrid power system, battery storage, and using that in an electric vehicle charging environment. So for that we've done some serious testing with CSIRO in their temperature chambers to look at the outcomes. So we've done some cycle testing at 20 degrees for one, and see and to check at the battery the effect on the battery temperature at different charge and discharge currents, or I should say at different discharge currents. So does this thing work? Oh yeah. Oh yeah. So here we see the 5 amp discharge, 10 amp, 15, 20, 25, 30, and 35 amp discharge rate to see what kind of effect that would have on the battery pack temperature overall. And you see that our battery pack performed quite well, and even at the higher discharge rate, and can therefore safely be used in this kind of application, so supporting up to 35 amp discharge rate. So we're having quite a good module performance for that kind of application. So second item under investigation is high temperature testing, and see what kind of what the response was soaking the battery for 12 hours in 40 degrees. So essentially your hybrid battery sits on a west wall, exposed full sunlight, and the entire battery enclosure, battery, everything reaches a temperature of 40 degrees Celsius. And then initiating the same test sequence as showed in the previous slide. So looking at different discharge currents. So we see the first graph here. This is the 5 amp graph. You see the temperature relatively stable, and then here after some time, then the discharge cuts off, and the module drops. The temperature drops down again. This is when the battery is recharged again, so it reaches a maximum temperature, and this is when the battery is the pack is fully charged, and then cools off again. So you see the different graphs. So looking at maximum charge rate of 25 amps, you see the temperature climbs very quickly, and then it cuts off, because this is the 55 degree is the temperature cut off, the limit. It's here. So, okay, so we do have a safety margin between the 55 degrees and the actual fully charged at 25 amp. So there's still a lot of, even at the 40 degree soak of the temperature, we still have some safety margin in the battery to cater for the performance of EV charging. We still maintain a high efficiency of over 90%. As shown by these tests. So the battery will give off more than 90% of the stored energy even under those conditions. And so the performance of this kind of battery is totally sufficient for solar or hybrid charging applications, as alluded to in the initial slide. So yes, we've shown that it is feasible. The next stage is constructing a prototype and getting some on-the-ground experience using essentially a home hybrid solar system combined with an AC charger to see how that would integrate into the home bundling. So overall considerations, of course, with any hybrid system are the availability of excess transformer grid capacity. So if you have especially larger scale systems, EV ultra-fast charging systems, you really need to make sure that you have access to that transformer capacity. I think that's something that Steve already mentioned for consideration in New Zealand. So is the site suitable for PV installation? Means will it be a ground-mounted system close to the EV charger, or can it be a roof-mounted systems? Lots of the petrol stations have, we see have flat roofs. Maybe a petrol station can be converted to an EV charging station. That would be a good usage, in my opinion. Of course, the next aspect would be to size the energy storage. You don't want to invest in battery capacity if you're never going to use it. Battery capacity is expensive, so that will really depend on the available capacity in the transformer. Of course, initially we'll have, as the EV fleet is growing, more usage will probably also require increased storage capacity to keep the grid impact as low as possible. So all in all, I think the emission reduction target needs to include renewable energy generation. If it's not already part of the energy mix, as in New Zealand, for example, in Australia, or especially in Victoria, where I'm from, with our beautiful coal-fired power stations, switching to electric vehicles is not really doing the environment any big service unless you invest in renewable energy at the same time. So if you can pair electric vehicle charging solution with renewable energy generation and battery storage, that would be a big improvement on the environmental balance overall. So yeah, that's all from me. My 5 cents worth. Any questions?